All right, recording has started. Welcome, everyone. This is day 3 of 5.11. This is our last lesson of the semester. We still have the review for this unit test, and we have the review for your final, but that's it. So this slide right here is from yesterday. Now, I did say at the end of yesterday's lesson that I would go over this slide because I only half finished it. I thought I was done with that lesson, and when I got to it during class, I was lost for words, to say the least. So I added to it. Also, I emailed everyone the PowerPoint because I did add some more stuff to it on different slides. I also added a very end slide of like kind of final thoughts that you may want to read. Also in the PowerPoints, below the slides in the comment section, I have links to Desmos for I think every equation that shows the demonstration of graphing the parametric and the rectangular equations that we did. So make sure you take a look at that. But I went ahead and this is what I modified yesterday on that slide. Let me just quickly go over it. So this slide pertains to equations, rectangular equations that are for circles only. When you have x squared plus y squared equals r squared, which is your radius is going to be 4, you want to use these two equations. And I went ahead and taking the example problem, x squared plus y squared equals 16, I need to get it in the form that looks similar to what an ellipse looks like, so it equals 1. So I divided everything by 16, which I showed here. 16 over 16 is 1, and then I just leave it like this. Now this is the form of an ellipse that allows us to see what the A and B values are. This would also apply to not just a circle, but also to an ellipse. Like if the equation was already in this format, you could easily pull out A and B. So looking at this, A squared and B squared, A is 4 and B is also 4. That's what I have here. So all we do is, knowing A and B, we just plug A and B into, well, these given equations. And that's how we get this. All right, and then to find your, I want to say parameter, your interval. Find your interval for the parametric. We plug in the domain restriction. Well, this one says interval is 0 to 4 for this, so I use 0 and 4. So this one's kind of tricky because if you type this in, we do the math, divide both sides by 4, we get this, we arc cosine both sides, and if you type it in, you'll get pi over 2. Well, looking at the unit circle, starting at 0, arc cosine of 0 is also equal to, I think it's 3 pi over 4. Where's my unit circle? Sorry, 3 pi over 2. Yep, 3 pi over 2. So, but that's going all the way around. So starting at 0, standard position, we rotate counterclockwise, and that's why I have negative pi over 2. And then I plug in 4, and I solve for that, I get 0. Well, this one's kind of tricky. It's not that straightforward with trig functions. So negative pi over 2 is the smallest value, pi over 2 is the largest value, so that's why the interval is that. But really, I wouldn't have known this. I wouldn't have known to rotate clockwise to get to this value unless I graphed it. So, and that's why my last slide talks about graphing it to be able to see what the interval is going to be. It really helps. And in this case, it definitely helps. So looking at this, because the domain is 0 to 4, this creates a semicircle, the right half of that circle. So in quadrant 1 and quadrant 4. So if you think about it, quadrant 1 and quadrant 4, it makes sense to have the rotation going from negative pi over 2 to positive pi over 2. So check the PowerPoint, click on the link, and you'll see what I'm talking about. But I promise you, you won't have something this, I guess, difficult or that requires this much critical thinking on your test or your final. So you can kind of relax there. Got a little carried away with this lesson. I thought it was super neat when I started working on it. Anyway, let's go on today's stuff. So 5.11, projectile motion. So if you are a fan of physics, if you took physics this year or last year, or you plan on taking physics, you will appreciate today's lesson. All right. Some people taking it next year. All right, being recorded. All right, projectile motion equations. All right, whenever an object is traveling in the air, that's called a projectile. It is moving in at least two directions, up, down, left, right. So we have the formula for the guiding equation of the projectiles in motion is h of t equals negative 1/2 g times t squared plus v sub 0 times t plus h sub 0. All right, g is the gravitational constant. Now, depending on the class you're taking, like physics will probably always use 9.8 meters per second squared as your gravitational constant. For this lesson, I noticed they use 32 feet per second squared. So I'm pretty sure every problem that I looked at in the modules, they use this constant. So keep that in mind, okay? V sub 0 is the initial velocity, and h sub 0 is the initial height. So, however, this rectangular equation we have, it only focuses on one or, well, both directions at the exact same time. So we can't separate distance and height with this rectangular equation because it's a quadratic, right? It's a parabola. It makes a U opening up or down. So that's the limitation of rectangular. Well, it's a good thing we have parametric equations. We can then separate those directions. We can now separate one equation will be the distance, and the other equation will be the height in respect to time. And here are the equations. Yep, so we have horizontal and vertical equations. X is your horizontal distance equation, and y is your vertical equation. And same thing, but now we have theta. Ooh, theta. And for these equations, it is important to know that you must be in degrees. So when you're typing this stuff in, you want to ensure that you are in degree mode on your calculator. It makes a huge difference. All right, no one should be confused yet. We haven't really done anything. I feel like I'm confused. Well, confused yet. We haven't done anything yet. Going over vocab and the two equations. You are not expected to derive these two equations like we did yesterday from that equation. It is given. All right. So as long as you understand that these equations represent projectile motion, this is the horizontal equation, this is the vertical equation, and then these are the parts of that. If you understand that, you're doing great. All right, first example. All right, volunteer to read this for us. All right, Emily, go for it.
I just want to say Rip Antonio, but anyway. Example, Adam Vinatieri, Indianapolis Colts, is lining up to kick a 50-yard field goal. He ends up kicking the ball at 45 miles per hour or 66 feet per second at an angle of 35 degrees. Will his kick reach the goalpost? For now, ignore the fact that the goalpost crossbar is above the ground.
Thank you. Thank you. All right. Football. All right. So we have two equations. We're trying to figure out, will the football make it? Any ideas how to set this up, or how to not necessarily set it up, but how to approach it? And just so you know, there's actually a couple ways to approach these problems. So there's not one way. So I'm not looking for one answer. I'm looking
Wouldn't
for.
we be using the formula you gave, the one that's affected by gravity? It's still on the first page, the half GT squared.
Yep. So we are going to use these. We are going to use these equations for sure. For sure, we're going to use these equations. And like I said, we are going to use 32 feet per second, or G. So that's a given. But how can I guess approach this? Like, what should I do? Any ideas?
First, we just take all the information we got so we know what to plug in.
Yeah, I think that is a great way to start this problem. So Antonio says, write everything down that we know. So let's do that. All right, what's our starting velocity, or our initial velocity, it's called? So I'm getting two answers. I see 0, I see 45 miles per hour. All right, so let's take a look at this. By the way, I only have two examples today's lesson, so we're going to spend a lot of time talking about this and the next question, just so you know. All right, so it says he ends up kicking the ball at 45 miles per hour or 66 feet per second. So if you're thinking the ball is on the ground or wherever is whoever's holding the ball, the tee, yes, it's not moving, so it's 0, right? It's not in motion, so velocity is 0. However, without motion, this problem wouldn't exist. So don't think of it just sitting there as being initial velocity. It's right when you kick the ball is what it's talking about for the initial velocity. So 45. Yep. So it is 45. And looking back at, oops, this page here. So we're talking about this equation. G is going to have feet per second squared. So this unit, feet. That's important. So remember, in physics and these word problems, you want the units to line up. Like if you're using meters, you don't want to be using feet. You want to be using meters and meters. If you're using feet and inches, well, you want them to both be feet or both be inches, not one or the other. Same thing with velocities. If we're using the unit feet here, we don't want to use miles. So should I use 45 miles per hour or 66 feet per second? I kind of gave it away, right? I meant, yeah, 66 feet per second. So for these word problems, you need to be careful of your units. And writing this stuff down to make sure you're using the same units really helps. So I put 66 feet per second. It might even be better if I wrote out feet per second so I can actually see the word feet in there.
Quick question.
Yep.
Will we always be given the conversion if we need it, or will we need to know the formula for it?
That's a good question. I'm going to say I'm pretty sure they give you what you need, like I did in this problem here. I'm pretty sure. But I will double check and let you know during the review for the test. How about that?
Thank you.
All right. What is the angle? 35 degrees. Yep. What is our starting height? 0. Yep. It's kicked off the ground, right? Mm-hmm. All right. What else are we given in this problem? So the length of the attempt, yeah. So the ball has to go 50 yards, right? So yep, we're given 50 yards. What's the problem with 50 yards? What is the problem?
It's very hard to make.
It's not in feet. Yeah, so we have to convert this yards into feet. That's very, very important. And I think most people know that there is 3 feet in a yard. All you got to do is multiply the yardage by, well, 3. 3 feet per yard. 50 times 3 is 150. So now we can see that we have the distance that we need to travel is in feet. Our initial velocity is in feet per second. That's good. All right. Let's see what we're doing next. All right. Do I have everything written down that we need? At least that was given to us? Yeah. So we wrote that stuff down. Now all we got to do is do what for the next step? Take a guess. Plug it all in. Yeah. So these 2 equations I have in the top right-hand corner, we're just going to plug that stuff into that equation. Now, we are going to use 32 feet per second squared for g. So what's negative 1/2 times 32? Negative 16. Okay, good. I didn't show that step. But that's how I got negative 16. All right, I will say that again for people who are zoning out and are watching this video and don't want to rewind it 10 seconds. All right, we are using 32 feet per second squared for the g. So negative 1/2 times 32 is equal to negative 16. That's where that came from. All right, all these word problems that involve projectile motion will start off this way. You need to write down what's given to you. You need to ensure that we are in compatible units. I'm going to call it compatible units. So like feet and feet, or meters and meters, or inches and inches. You want to make sure it all kind of lines up. We don't have mismatches. And once you have that all set up, we plug everything we know into those 2 equations. And then the fun is going to start. Everyone's good so far? Okay, good, good. All right, now we have to make choices. Now, any ideas of how we could approach this? So remember, we're trying to figure out if the ball made it to the goalpost, right? So how can we approach this? Now, just so you know, this is a 2-part problem. We can't actually solve this in one, I guess, one setup and solve part. It's going to be two parts. So there's kind of a hint. And here's another hint. You want to use one of the equations for part one and then use the other equation for part two. So with that said, what do you think? Find t using x. All right, expand. Caitlin. How can we find t using x? Use the mic or type, however you want. Solve for x in the x equation. Okay, but here's the problem. In that first equation, the x equals all that stuff, we have the variable x and we have the variable t. So in order to solve for what you're saying solve for, just make sure. To solve for t, we need to know what x is. But you're on the right track. You're like, your thought is halfway there. It's not wrong. You're just halfway there. You are on the right track. So expand on that idea. Because it's not wrong. Solve for t using x. So all of you are on the right track. You're missing one little piece. Emily, go for it. Take the mic.
Okay, so would you solve for, like we did yesterday, solve for t in terms of x and then substitute it into the y equation?
Sort of yes. Sort of yes, but we actually need to have an actual number answer for t. We just can't have t equals all this stuff with the variable x in there like yesterday. We actually need to solve for t in what you're describing. You are on the right track. Okay, so let me see here. So does it have to do something with the one? Yes, Caitlin, it does. So Caitlin says, does it have something to do with the 150 feet? And the answer is yes. And she says, because the distance needed to travel, and that is correct. So isn't x 150? Chloe says that. So, yep. So we want to solve for t when the distance is 150 feet. Ooh, that is basically what you are saying. So we are plugging in 150 in for x because that is the distance we need to kick that football. So everyone on your paper, quickly solve for t. Everyone, quickly solve for t. I'm going to give all of you, let's do 1 minute. Probably less than 1 minute, but I'll say 1 minute. Everyone solve for t. Because it was too much pressure, Julia.
What should we round to?
Give me 2 decimal places.
Okay, thank you.
All right, time is up. What did all of you get? 2.77. 2.77. That is correct. That is correct. 2.77. I'm going to quickly show the math of what I did. You know, you take 150, divide it by, well, 66 cosine 35. 0.77. Okay. So it's going to take 2.77 seconds to get to 150 feet. Now, does that imply that it actually gets there? Careful of what you say. So, got a lot of no's, right? Got a lot of no's. Can you justify why it's no? Like, how can we solve? We set x to 150. The time it takes is 1.77 seconds. How is it possible that it won't get to that distance, even though we found the time that it will take to get to the distance? Kind of a confusing question. That would be the time. So Antonio says that would be the time of the ball to hit the ground. Not necessarily. So 2.77 seconds doesn't mean that's the time it hits the ground. It doesn't take into account where it's in the air. You're right. Yeah. So even though distance-wise it gets to 150 feet, we don't know if the ball is in the air, which is actually maybe a good thing, right? If it's still in the air, it means it probably went through the goalpost, ignoring the height of the goalpost. But the thing about this is a quadratic. It's a parabola. It makes a U, right? Is it possible that at 2.77 seconds that it reaches 150 when it's underground? Well, it won't actually go underground, but mathematically, if we created that quadratic and we graphed it, the path that it takes would show that it's underground. So at 2.77 seconds, we don't know if the ball is still like in the air, if it touches the ground exactly at that time, or if it's underground mathematically. So part 2, what do we do with part 2? Yeah, you just substitute into your y equation. Okay. So what I did, and because I'm really big on using exact values, instead of putting 2.77 here and here, I put in the previous step that you would have typed in. And this way it keeps it in exact values. However, on your test, on your quiz, I'm going to say it's probably okay to use this rounded value in this place and in this place. It's really not going to change the answer we get dramatically. We're not talking about money here, okay? This is about location in space. So if some of you want to use 2.77 here and type it in and hit enter, let's compare the answer that I get using exact values versus your 2.77. I'm actually curious because I didn't try it. All right, Julia, you used 2.77, and let's compare. You probably will be maybe spot on to my answer, or maybe off by like 1/100th of a point, and that's probably okay. Oh yeah, not using rounded value is always the safest way. Yeah, if you can avoid using rounded work, do. But sometimes you can't avoid it. All right. So everyone type this in, hopefully you're done typing and hitting enter. Go ahead and put the answer. What is the answer in chat? So we got negative 18.13. Anybody else want to type it in? All right. One person typed it in. Lovely. Ooh, Desmos. You should probably use a calculator instead of Desmos. It might be too much for Desmos to handle for whatever reason. Julia, there's no way that is what you got. Julia, make sure you are in degree mode. All right, let me just show my work here. All right, so I simplified mine. You don't have to do this. I just use the stuff we learned in the last couple units. 66 and 66 cancel out. Sine 35, cosine 35, they are the same degree. And sine over cosine, same thing as saying tangent. So sine 35 over cosine 35 equals tangent 35. And like I said, 66 and 66 canceled out, and then 150 still on the top. So I just simplified this. You don't have to do this. I did.
I did it with 2.77 instead, and I got negative 17.90.
17.90. Negative 17.90. So you were off by like, I don't know. Math is hard right now. Like a quarter of a foot, it looks like. So it's close, but it's definitely not that close. I thought it'd actually be closer than that. So one thing you can do to minimize the percent error, instead of using 2.77 seconds, bring out this decimal to like 5 or 6 places when plugging it into here, and that will minimize your error. Your percent error is called. All right. So at 2.77 seconds, the ball is at negative 18.13 feet. What does that tell us? Now we have to comprehend what's going on. So what does that tell us? It's underground, so it didn't make it. Yeah, the ball did not make it. And I went ahead and I drew this. I did this really sweet PowerPoint art of showing this football, and showing the ground is the green, and that at 2.77 seconds, we are 18.13 feet below the ground. So it gets at the goalpost, but it's below ground. So based on my picture, it is clear that it hits the ground here at some time, and the path would make it to the post underground. So the football did not make it. Does anybody know the record for the longest successful field goal kicked in the NFL?
60 something yards. 64, I want to say. Sounds about right.
Someone Google it real quick. Someone Google it. I thought it was like 55 or 50.
I was dead on. I know football. Matt Prater did a
64.
64
Oh
yard
boy,
field goal.
64. All right. All right. Yeah,
I was spot on. Let's go.
all right, 64. All right. So same problem. This we're going to do this problem, the same problem, a different way. Instead of finding the time it takes to get to 150 feet in the x direction, we're going to find the time it takes for the ball to hit the ground. Ooh, that'll be neat. We're going to find the time it takes the ball to hit the ground. So when the ball hits the ground, what does the height equal? 0. Yeah. Yeah. So we're using the y equation. We're setting y equal to 0 because we want to know when the ball hits the ground. All right. Negative 16t squared plus 66 sine 35 plus, or sorry, times t. How do I, this looks nasty. How do I solve for t? Yes, Chloe, you are correct. The quadratic formula. Solving by factoring would be it would be a pain, really. Yeah, the quadratic equation. Well, actually, no, I did solve by factoring. Okay. So, Chloe, you are correct about using the quadratic formula, but we could also use factoring in this case. Either way is fine. And we're actually going to use the quadratic formula on our next example. So the reason why we can use factoring is because your initial height is 0. So if I had like plus, I don't know, like plus 10 after this, I would have 3 terms and I could not solve by factoring. But because it's plus 0, I can factor out a t, set the factors equal to 0, and solve. So that's why that works here. All right, so t equals 0. And then I solve this one, subtract the sine stuff, both sides, and then divide everything by negative 16. So I'm just going to quickly show this. All right, everyone type that in and hit enter. You probably don't need it. Don't type in these negatives because a negative divided by a negative is a positive. So just type in 66 sine 35, all of that in parentheses, divided by 16. It'll save you some typing. So a lot of 2.37s, 2.37s. That sounds right. 2.37. So that means, using my same picture, it takes, oops, I gave the answer away, dang it. At 2.37 seconds, the ball hits the ground. For this part 2 that I already showed you the answer to, we need to find out what that distance is when it hits the ground. Hopefully, it's 150 or more, which means it would have actually made it to the goalpost. But if it's less than 150, obviously it means it is short of the goalpost and did not make it. So we're going to plug in t into your x equation to find the distance. And again, I'm using exact values here. You can probably plug in your 2.37 and get somewhere near that. But using exact values like that, I got 127.92 feet. And that's why I have that labeled. Oh, and then I also have this box uncovered from the previous work we did. So 2 ways to approach it to give us different values to help us make the decision if the ball made it or not. And in both scenarios of how we approached it, it is pretty clear it didn't make it to the goalpost.
Can you go back to the last slide so I can take a screenshot quick?
Ooh, I have a Desmos link. Let me pull that up.
Thank you.
Ooh. All right, I'm going to share this with you. I think it's really neat. I made a Desmos simulation thing. Pull it up. Right, everyone should see my Desmos. 150 feet is just over here. And you can see from this, my equations that I typed in to model this scenario, it's all here. I'm not going to go through of all this stuff I typed in, other than the fact that you can change your values, like your initial velocity, your A and B, which you can kind of see what those values are up here. I have G in there for your gravity, which is negative 32 feet per second squared. All right, so everything is entered properly. A is 32. Is 32 the angle? Was it 33? I feel like it was higher than that.
It was 35.
It was
Oh, it's 35. Okay, I got to change that then. Okay, let me change that. And then B is, so B is your time, it looks like. Just trying to see what I did all those weeks ago when I made this. Okay. So in Desmos, I can't be using the same variable to represent a different equation here, but I'm guessing that's red. My red dashed line is the actual path of the ball, which you can see it doesn't make it to 150. It hits the ground at, well, I think we said 127. My blue, it trails my actual football, which is this line here, and then I can change. I hit play. Ooh, we love animations. There's the football. Look at that. The path of the football represented in Desmos. How cool is that? And I can actually stop this, so I can move this point like here. guess maybe exact. And I click my point, it tells me roughly where it's at. It's kind of neat. So if you want this link, I will share it with you in chat. You can play with that and save that. Let's go on to our last problem. And again, we're definitely going to go over today. So if you have to go to your next class at 11, please do, and just come back and watch the recording later. Sorry, I'm really bad about going over time. I know. Time flies when you're having fun. All right. Next problem. Antonio, read this one for us.
All right. Michael Jordan is trying to hit the game-winning shot at about 6.5 feet tall. His shot occurs 7 feet off the ground. The height of the NBA rim is 10 feet. What time running out? He must shoot the ball at half court, 47 feet away. If he shoots the ball at 40 feet per second at 40-degree angle, will the shot make it to the rim? Not go in, will it make it to the rim?
Yeah. We'll make it to the rim. All right. So let me just quickly, for time's sake, I'm going to write down what we know. We know the initial velocity is 40 feet per second. We know the angle is 40 degrees. We know your initial height of the ball is 7 feet. We also know that the rim is 10 feet off the ground and that we are 47 feet away from the rim in the horizontal direction. I didn't write those down, but I should have. All right, so we're going to plug that stuff in. Just saving time. Plug that in. And then just like the last problem, you have two ways to approach this problem. You can look at it as, let's calculate the time it takes to get to the distance needed, or we can calculate the time needed to get to the height we need. So for this page, let's find the time it takes to reach 47 feet in the horizontal direction. So let's do that. Everyone find that. The time it takes to reach 47 feet in the horizontal direction. So we got, some people in chat, 1.53 seconds. Just do two places is fine. So we got two people said 1.53, 1.45, 1.53. Julia, check your math. Might have entered something wrong by mistake. It is 1.53. So there's the math. Right. So 47 feet. Distance takes 1.53 seconds. Now let's see if it gets to the rim. All right, so we're gonna use the height. And again, you can use 1.53, but you actually want to use a much larger or longer decimal that's out to like 5 or 6 places to be closer to the exact answer. So probably like 5, 6, 7 decimal places would be safe. But the safest is to use the exact, which is 47 over 40 cosine 40. And again, I went ahead and I simplified mine, just like the last problem. So here's the thing here. Oh, never mind. I was having a different thought. Next page. All right, type it in. What do we get? Everyone type it in. Can you swim? What's your calculator, Julia? Windows. My guess is you probably. So in Windows, you need to make sure that you do 47, your divide sign, parentheses, 40 times cosine, parentheses, 40, in parentheses, enter. So Julia, let me type what I just said. 47. Times All right, Julia, if you're using Windows, you should have typed that in. All right, so people got 8.79 feet. All right. I think that's what I got. So based on this, can you say it got to the rim? Well, you can't be certain. Now, here's the reason why. So even though at 1.53 seconds, it says the height is 8.79 feet. What if it actually got to the rim and went through, and then that is the height of the ball right when it went through the rim or the hoop? So for this problem, it's not as clear until we look at it the other way. But based on what we have here, it does look like it's too short, right? It totally missed it, right? So he's like, no. So, based on what we have here, it looks like it just missed it. It was below the rim, and, well, his team lost. Rip. But let's look at it the other way. Instead of finding the time it takes to get to 47 feet, let's find the time it takes to get to 10 feet. I think that'll be a better indication whether or not it actually made it or not. All right, so same idea. We are write down what we know, but this time we're going to find the time it takes for the ball to get to 10 feet in the air or vertically. So for this problem, we need to subtract 10 both sides. Why didn't I show that? Oh, why am I so bad sometimes? Uh-oh. I messed this problem up. You know, when I present, it's clear to me when I make my mistakes, and I made a mistake. Yikes. I totally messed this up. The work is wrong. Oh, that's such a pain. So I should have subtracted 10 both sides. Let me go ahead and write that down. I wish I could just change it in PowerPoint, copy and paste it into Neuro, but Neuro doesn't have that needed feature of pasting stuff like Google Jamboard. All right. So I should have subtracted 10 both sides. And we get negative 16 t squared. So 7 minus 10 is negative 3.
Do you want me to black out everything?
No, you can just black out that 7 on that next line, and I'll write in a negative 3 instead. So that's the only piece of my equation that is wrong, but that dramatically changes the answer. That should be a negative 3 right there. Whoops. I'm surprised I totally missed that when I wrote this. All right. So everyone go ahead and type that in and tell me what you get. That's so frustrating. Antonio, block out just those numbers. So we're gonna have to, those are wrong. Well, move your box over so it shows the t is about equal to symbol. Thank you.
You're welcome. Neuro hates me, making me like 3 boxes. I don't know why.
It hates me every day. So 0.13. I wonder if my work was right on my paper and I just didn't type it right when I typed it on the screen. Because I got 0.13 as well. All right, Antonio, just kidding. Delete those boxes. Those values actually might be correct. They are correct. Okay, so I did the math right when I typed it in. I just didn't type it right on the screen. Well, that's nice at least.
So now this is you down here?
Yeah, the math is actually right. This what I
I got
have.
an
Yeah, so it's
error.
fine.
I don't know why I got an error.
You probably want to check your formatting. That's most likely what it is.
Yeah, I've checked it over and I wrote negative 40 sine 40
So real quick,
plus
what calculator are you using?
the Casio FX150.
So
Yes, plus.
and you're hitting your Casio, it has a dedicated negative sign, but it also has the minus sign, and they are very different. Are you using the actual negative symbol? So the actual negative symbol is right below your fraction symbol on the upper left. It's in parentheses. That's your negative symbol you want to use. Right. So making the assumption you use plus instead of minus, you can't really. I would say it's a good guess, and you're probably right, but you do want to type both of them in to get both answers. So this first time is about 0.13 seconds. This is when he shoots the ball. Remember, it leaves his hand at 7 feet in the air, so it takes about 0.013 seconds for the ball to first get to 10 feet, and then it's still traveling upwards, and at some point it starts traveling downwards, and then at that time it hits at 1.48 seconds, it's back at 10 feet. So really using this step and looking at it takes 1.48 seconds to get to 10 feet, and then going back to the previous problem and seeing it takes 1.53 seconds to get to the distance we need. So 1.53 to get to the distance we need, but at 10 feet, it's 1.48 seconds. So this is less time than this one. So with that information, it implies that we're not 247 feet yet in the horizontal direction, based on the fact that this time is needed, and this is what we calculated right here for the 10 feet. So making the conclusion that he didn't make it was actually true. But anyway, let's go ahead and just finish this problem just to show that. All right, we're going to plug in that 1.48 seconds into your t. Now, in this case, you really don't want to use the exact value. Like, I don't want you to put t as that entire quadratic equation. That would be crazy. So in this case, I would say it's probably acceptable to use the 1.48 and not that entire quadratic line, unless for whatever reason you really want to, just to compare the two. But I use 1.48.
You can actually use the whole thing if you have a calculator that lets you, because I figured out why I got an error. I had forgotten the parentheses, but if you do answer times 40 cosine 40, then you don't have to retype the whole thing.
Right. And there's also, depending on which model you have, you can actually, when you type that quadratic, hit enter, you can actually store those values into memory as the exact answers. But I didn't go over any of that this class, just because not everyone has the same model, and I don't really want to explain it for like 6 different models. But yes, Emily, you're correct.
Yeah.
Once you type it in, you have your answer. You type in this next step. You want to use the answer key, and that is a way to get the exact answer in there.
Yeah, I always use that instead of trying to just retype it.
That's smart. That's smart.
Annoying.
That's smart. So based on 1.48 seconds to get to the height of 10 feet in the air, the horizontal distance is 45.35 feet. And we know the rim is 47 feet away. So based on this way of doing it, it is definitely clear he didn't make it. And I have a really cool Desmos for this one too. So let me show that, and then we'll be done. All right, so I created the Desmos after I did the problem, and I did that picture, not knowing that he was shooting from the right, shooting to the left, and I didn't want to change my picture because it took me a while to do it. I just didn't want to redo it to represent the actual direction. So, yep, there is the path of the ball. And we can see that it needs to get to 47 feet, which is about like right here, 45, 46, 47. So that's 47 feet right here. Let me pause this, move this over. So let's see, 45. I hope this, is this the right equation? Hold on, let me see. Oh, no, see, I didn't update my Desmos. This should be -3, and this should be -3 too. That makes sense. All coming together. Right. So let's see.
But now isn't he shooting underground?
Well, that's the path, right? So at one point, X, Y. So what was the time it took to get 10 feet again? Get Antonio?
Was it the 1.48?
48. Okay. So I hit enter. 1.48. It is at a height of 6 feet, distance of 39.4 feet. Dun, dun, dun. Assuming my equation is correct. Let's see, 40 cosine. I feel like it's not typed in completely correctly. 40 cosine 40t, 40 cosine 40t. And then 16 t squared plus 40 sine t, t, and then, oh no, that is right. I was right the first time because we're using the original equation here, not my quadratic one. It didn't look right. Okay, so this is right. All right, so 1.48 seconds puts us 16 feet above the ground. This can't be right. Someone tell me if I typed this in wrong.
To be honest with you, I'm lost.
Caitlin was saying she used 1.53, not 1.48.
Dun, dun, dun. Tabbing back and forth to make sure I typed it in right. 16t squared. Huh. And everyone got 45.35 feet? Is that right? I'm hitting this in my Desmos. I don't know. Try using 1.53. Okay, let me use 1.53. All right, 1.53. It's 15 feet above the ground. Huh. Doesn't make sense.
Haha, no.
So it reaches 10 feet at 46.84. I'm lost. I'm confused of why it's not working out. Let me look at this, and then I'll probably email everyone of what is going on with Desmos. I don't know. I do not know. But that's okay. I'll figure it out. But other than that, we have the math here, and assuming the math is typed out right and the answers are right, this is good.
In my opinion, it's probably the hardest lesson of this entire unit.
I don't think so. I don't think it is.
If you understand physics, you probably understand it a little more, but definitely
These-
needs practice.
These problems are done pretty much the same every single time, and you have two ways to approach it. You know, you either find the time it takes to get to the distance you need, or the time to get to the height you need for your step one, and it really doesn't matter. Some ways are going to be easier than the other. And then your part two is to plug in your time into the other equation to find that. And then once you have your two answers, the time and then your distance, whether it's horizontal or vertical, you use that to compare it to the word problem to see if it actually meets the requirement that you're trying to get to. So if it does, then yeah, it does. If it doesn't, it doesn't. Drawing pictures helps. Creating Desmos that are actually accurate, which I need to kind of mess with this problem to figure out what I did wrong. I'm not sure at first glance, but I'll figure it out and let you guys know. Other than that, any other questions? Nope. Well, guys, thanks for hanging around, and I hope you learned something in this class. A few things. And we will go over the review tomorrow. All right, take care.